Hi, Mrs. Pone here, and today we're going to look at some periodic trends. And this is going to be broken into two screencasts because it's going to be pretty dense in terms of material. But we're going to look at a couple things. We're going to look at nuclear charge, electron shielding, atomic size, first ionization energy, electronegativity, and reactivity. And we're going to look at all of these things in terms of Coulomb's law. And you should have just watched the presentation on Coulomb's law and just recall that opposite charges attract, like charges repel. The more charge, the greater the force of attraction. The more distance between charged particles, the weaker the force. So electric charges behave kind of like magnets. The bigger the magnet, the stronger. The further apart the magnets are, the weaker they get. And like charges repel, opposites attract. And this was Coulomb's law. So Coulomb's law is the underpinning for our understanding of nuclear charge and electron shielding. This video, we're going to talk about these two things. And then in the next slideshow, we're going to explain trends in all four of these things in terms of these two things. So there won't really be any need to memorize these things, but you're going to have to understand nuclear charge and electron shielding and know what these things generally mean. So nuclear charge, what is nuclear charge? Well, it's exactly like what it sounds like. It's the electric charge of the nucleus of an atom. And it's equal to the number of protons because the nucleus of an atom is filled up with protons, positively charged proton particles. And the nucleus is what attracts electrons and keeps them in the atom. And what can we say about the charge of the nucleus as we move across a period in the periodic table? Well, let's say we're down here at lithium. Lithium has 3 protons, so there's a +3 charge in a nucleus. Beryllium, +4. And as you go over, +5, +6, +7. The positive charge in the nucleus of an atom is getting bigger. It's increasing as we go across the periodic table. That means the pull of the nucleus is getting stronger. Likewise, as we go down the periodic table, we go from hydrogen, which there's just +1 in there, to lithium with a +3, then sodium, +11, and so on. The pull of the nucleus is also getting stronger as we go down this way. So nuclear charge kind of increases, not kind of, it does increase both ways in the periodic table. If you're going down or across, the pull of the nucleus towards electrons is getting stronger and stronger. And I guess one way to look at this is imagine this was a proton and a tug of war, and it's trying to pull an electron to it. Well, one proton is going to pull an electron, but what if we had 2 protons? They're going to have to pull a little bit stronger. If we had 3 or 4 or, I don't know, 50. Keep going and going and going. The more protons, the more they're going to pull. That's Coulomb's law. The greater the charge, the greater the electrostatic force. So the more protons we get, the stronger they can pull on electrons. So that's going to be true. So nuclear charge increases that way. It also increases down in the periodic table. Increases both ways. Now let's look at what happens as we go down a periodic table. And we're going to draw Bohr diagrams with electrons. And we see that hydrogen, there's 1 electron. It's a 1s1, 1 energy level. As we go down to lithium, now there's 2 energy levels. And the 1s2, 2 electrons in there. These are right here. Then there's 1 electron in the 2nd energy level, right here. And going down to sodium, oddly enough, now we have 1, 2, 3 energy levels. Energy level 1, energy level 2, energy level 3. In each case, as you know, in column 1A, there's 1 valence electron, 1 outermost electron in the outermost energy level. The outermost shell has 1 electron. So that is true. And what do you notice in terms of a pattern as you're going down the periodic table? Well, the number of energy levels is increasing. As you go down a period in the periodic table or down a row, you get an extra energy level with every jump. And this is going to be true for all 7. There's 7 periods in a periodic table. Each jump is going to correspond to a new energy level. This is sodium. If we jump down to potassium, there's going to be another ring. If we jump down to rubidium, even another ring. Until eventually we get down to francium and there's going to be 7 rings. Every row going across in the periodic table corresponds to a new energy level. And again, just to refresh, this is kind of based on the electron configurations. Remember we saw those a repeating pattern of electron configurations? This ends in 1s, 2s1, 3s1, 4s1, 5s1, 6s1, and then 7s1. And there's a whole bunch of patterns following this Aufbau orbital configuration. And now let's look at what happens to energy levels as we go across the periodic table instead of down. So lithium is going to have 3 electrons total, 3 protons if it's neutral, 3 electrons, 2 in the first energy level, and 1 out here. Beryllium is going to have 1 additional electron. And again, we didn't add an energy level in this case. All we did was we added an extra electron. Compared to this atom over here, beryllium has 1 extra electron, but the same number of energy levels, 1, 2, 1, 2. And the same thing is going to happen for boron. Before I show the picture, we're just going to add 1 more electron here. Same number of energy levels. So as you go across the periodic table, you're just adding electrons to the same energy level. The number of energy levels remains constant as you go across the periodic table. Very, very important. But notice the pull of the nucleus is getting stronger. That's going to be very important for a little while. And now we're going to talk about electron shielding based upon what we just saw. Electrons in an atom can shield one another from the pull of the nucleus. This is a sodium atom, and hopefully you picked up on that by its plus 11. There's 11 protons in here. They all have a positive charge, and they're pulling all these electrons in. They're saying, hey, get in here. But what's going to happen? This electron right here, the nucleus is pulling it in. But this electron right here, what do like charges do? Well, they repel. This electron saying, hey, buddy, get away from me. So this electron right here can't feel the full pull of the nucleus because it's being shielded or repulsed by this electron. In fact, this electron right here is being repulsed by every single one of these electrons. Because remember, these electrons are actually moving around the atom at high speeds, and this isn't exactly what an atom looks like in these concentric shells. But this electron's moving around, it's repulsing it. Every single one of these electrons, there's 10 electrons in between this electron and the atom, and they are repulsing this electron. They are shielding it from the pull of the nucleus. It can't feel the total pull of the nucleus. Even though the nucleus is attracting it, those other electrons are repulsing it. So what can we say about shielding? As you go down a group in the periodic table, shielding increases. Why? Well, are there any electrons shielding hydrogen? No. The nucleus is pulling it in, and there's nothing there. Now, if we look at lithium, this electron right here, it's being shielded by 2 electrons that are in between it and the nucleus. So there's more shielding. As we go down to the next level, we have sodium. And this little guy right here, well, he's being shielded by 10 electrons. And they're all moving around, they're all repulsing it. So the amount of electron shielding is increasing as we go down. And if we drew this for potassium, it would be this energy level would be full, or it actually wouldn't be full, it would have 8 electrons in there, and you'd have another ring here. Then this lone electron for potassium would be repulsed by 18 electrons that are in between it and the nucleus. So electron shielding is going to increase as you go down. As you go across the periodic table, shielding is going to remain constant. Why? Well, this lithium atom, it's being repulsed by 2 electrons that are in between it and the nucleus. This electron is being repulsed. There's only 2 electrons in between it and the nucleus. And also this electron is being repulsed by these 2. And when you go over to boron, all 3 of these electrons are only being repulsed by the electrons in between them and the nucleus. So the level of electron shielding is constant going across. It doesn't increase, it doesn't decrease, it stays the same as you go across. As you go down, there's more electron shielding. So these are the two trends that we've just seen. As you go across the periodic table, nuclear charge increases, the pull of the nucleus gets much stronger. As you go across, the level of electron repulsion or electron shielding, it stays constant. You're just filling up an energy level. You're not getting additional energy levels. As you go down the periodic table, the nuclear charge is still increasing. The pull of the nucleus is getting stronger and stronger. But electron shielding is increasing every row you go down. You're adding a new energy level. Sodium would be 3. Potassium would be 4. You're getting more and more electron shielding, electrons that are repulsing one another. So you can't feel the total pull of the nucleus because there's other electrons that are shielding you from it. And I hope that gives you a somewhat decent understanding of how Coulomb's law relates to the periodic table. Again, like charges are going to repel, opposites are going to attract. And we're going to have trends in nuclear charge, and there's going to be some shielding trends. And we're going to apply both of these to 4 other things. And really, these 2 things are of monumental importance to understanding the periodic table. So hopefully you have at least a decent understanding right now of nuclear shielding and our electron shielding and nuclear charge. This is Mr. Spohn. I'll see you in the next video.